if somebody is interested in the topics, I think this is a huge and very important resource also for communication of what we are doing. And this looks kind of strange. It's so small. Yeah, this is a new screen, haven't seen it before. Okay, so please speak loud so that I can also record your audio. And otherwise, please start your presentation.
Okay. Yeah. Good morning, everybody. My name is Danny Chucic, and my presentation, my bachelor thesis is inclusive networking. It's a web-based system for anxiety-aware people and on-site event networking. So, the real problem is networking events happens on cafe, conference, meetups, and are core part of professional life. But rarely, but they rely almost entirely on spontaneous conversation between visitors, and most of the people who have social anxiety or introverts or something like that, there happens the first barrier, and this app should work as an icebreaker for that. Even though those people have valuable expertise in different topics, they mostly don't have. They mostly leave earlier from those events and don't say a lot. And as the picture shows, they are left out. And what I want to say, anxiety aware is design constraint here. It's not medical diagnosis or something like that, because we are from IT sector. There are established tools in this space, for example, like Meta, LinkedIn Events, or B2Match. They use mostly QR code for access control. But the real gap with my work is they don't combine three things together. It's first one is interest-based grouping. Second is anxiety-aware interaction design, and deployment with no dedicated hardware. There is no cost and can be deployed today, so to say. Because I and Professor changed the topic a little bit during the work, we introduced the AI into this topic, and that's also even bigger gap, because it's not every time very clear how AI models group the people according to their interests. And so we come to my research questions. There are three. First one is, how can a low barrier anxiety-aware web system really structure on-site networking to lower the first contact barrier for people who have a problem with that? Second one is, when a general purpose, and that's the core of the work, when general purpose LLMs are the grouping engine, how does their behavior differ, and what does it mean for inclusion of every visitors from an event? And the third one is, can such a system be deployed today with minimal or no barrier or no dedicated hardware? The solution for those research questions is my app, and the flow of the app is intentionally left so minimal. Everything what the user needs is Matrix account. Matrix is most of you probably know, it's a protocol for messaging. I use it here a little bit differently, but anyway, you need a profile, with at least 3 interest. It can go up to 10. Host of the event can create event, and you choose which AI model will group visitor's interest. And he, after creation of the event, he gets a QR code which can then be distributed as any way cost 1. It can be downloaded as PDF or SVG. During check-in, every visitor can choose between three modes of check-in. It's automatic. The system assign the visitor to the best table. The visitor can pick a table if it's free, or he can choose say to be seated at an empty table if he comes with group or some friends. Here comes AI models. They do the grouping of the people to the table, and at the same time they create topic conversation according to the interest of those people. I want to say the core idea was also to create floor plan navigation, but we gave up in order to do it with AI grouping and topic generation. Architecture used for this work is lightweight and serverless. You don't need any dedicated hardware except mobile phone to scan the QR code at entrance. For frontend, I use React framework with TypeScript and Tailwind instead of CSS. Frontend is hosted on Cloudflare pages, and backend is also hosted on Cloudflare workers for backend. It's done also in TypeScript and works. Yeah, it's serverless logic. There's a bot, matrix bot, who triggers the backend, do the work, and yep, that's pretty much what backend does. As I earlier said, I use matrix protocol as database in this case, some sort of database where everything that happens is stored in a room as a state, and every event represents one matrix room. AI models which I use are also from Cloudflare, because Cloudflare offered really good free tier for work. There are differences from ChatGPT, Meta, and so on. Important to say is that host can choose between, I put 6 or 7 different models which can be used to group people at the event. I also done 3 case studies in 3 different three different means. Yep. First one is IT security and conference. The second one is HR conference, and the third one is Expo Tag at Wirtschaftskammer. I chose randomly Llama, Mistral, and Quen. Llama is from Meta, Mistral is from France, Europe, and Quen is from Alibaba from China. They are different by size. Llama is the lightweight model, and Mistral is a bit bigger, but anyway produced some mistakes, and Quen is a bigger model and produced the best cases in my case studies. There is a pattern to recognize, because Llama left every time first person alone at a table, which is really bad, because that's what we want to that's what we don't want to do yet. And important to say, expected it was 7th person, P7 was also from those domains, but it was actually some edge case based on their interest. Mistral left every time to that 7 person alone, and with Gwen, it never happened to anyone be left alone. In conclusion, my contribution to this work is deployed no hardware dependent system for on-site networking, which works as an icebreaker. During those 3 case studies, it was clear to see that it depends on which the results or grouping and topic generation depends on which AI model has been chosen. And I want to say the scope of this system was system design, architecture, and exploratory study. It at the beginning was planned to do indoor navigation, but we gave up from that. And I also would like to show what I have done. That's the landing page. Sign up leads to, in this case, because I'm already logged in, element. If you don't have a account, you go to register. As I already said, interest can be set at 10. You can reach me, second, first, last name, email, even avatar can be paused, but it has to be image, of course. During network event creation, you can choose some of those cloud hosted AI models. Number of tables or visitors to tables can be also chosen, and there's a list of events already existing. Those are my case studies. If you open some of those case studies, you can see people. It's a little bit small, but you can look which people are assigned to this table and their topics. Everybody can leave, because we are host now, we can delete events. And as a normal visitor, you can leave at any time. I want to say every time you leave, any person who leaves, topics are generated again according to those people who are left or still at the table. Yep, there's a QR scan. That's pretty much everything.
Okay. Are there any questions?
Maybe you say it, but I didn't hear it. Like, what happened when someone leaves? Like, someone else come on the table, or it's like?
Topics are generated again according to those interested people who are still at the table.
So no one new will come to the table. It's just like if someone leave, no new members are coming.
Well, it depends if there's someone. Even the person who left can be also signed again.
Okay, interesting. Thank you.
Did you evaluate, like, where you showed like the groups and the distribution? Did you evaluate it with actual people?
No, still more. No.
Oh, okay.
I want to ask everybody here if I can write to you. It was Professor's idea to write to colleagues and to ask for 3 interests, and then record what happens every time I sign a review. And if you are satisfied with your where you have been assigned or not, at the moment of check-in and after the event, so to say. That was the idea. Maybe if you have time to have those 3 interests, I'd like to do it. Yeah.
Because I was interested if the suggested talking topics are actually picked up by the people. also not necessarily the distribution, but because you also introduce these generated topics.
Yep.
And that's what I was also interested in, if that was like analyzed.
Well, it was just a second. Test account. Maybe something topics from export target jobs comma. Every person has some random topics, and interesting to see it's here. Like Quen, yeah, that's the table. Quen produced German topics for one table, as you can see. All the two are in English, so I'm sure it's also. Here was on must. First one table is because it takes every time people's interest and create those topics. Those are some functions or something like that, but yeah, it's anyway interesting to see for case studies. But it uses people's interest.
Yeah, maybe a few words to the case studies that you carried out, because you have IT security conference, HR conference, and export doc.
Yep.
So, and that's that kind of the focus. Is there a focus of the conference? With an IT security conference, you have a very narrow focus, so people have a much smaller space of interests. HR is more broader. There can be a lot of stuff in there, but still it's focused on HR. And export doc is like no focus at all. So it's like the whole life, every business can have it their own topics. So we try to come up with these kind of different scenarios and test whether the large language model finds common ground for discussions.
If someone is interested in people's interests, I choose for, but I have no place for that. If we have time still to show quickly.
Actually, we have to move on because there's so many people. So thank you very much, and we will move on.
So just short interruption.
Yeah.
I think there are 2 people outside the
Oh,
door. I hope this
really?
is-
Okay.
Oh, okay.
Probably wanted just to enter the room from. Okay. Do we have the signature forms somewhere? Ah, here. Okay.
So yes, I present a system for real-time 3D world generation. So what my system basically does, it takes OpenStreetMap data that is freely available and uses the building outlines and other features that are present in the data to generate a 3D world, which is basically explorable in a real-time engine. And there have been similar work has been done in this field already. So, for instance, there are several input plugins for game engines like Unreal or Godot, which basically can import OpenStreetMap data, and then the game developer can basically iterate on this data further. Other than that, there are also 3D, simple 3D renderers for the OpenStreetMap data online to explore it, like Google Maps, but in a 3D environment. And probably one of the best solutions currently is by Black Shark AI. They basically developed the work generation for the Microsoft Flight Simulator. And this approach basically takes machine learning from satellite images to annotate where, for instance, a building is, what roof type it has and such, and it sends to the client this metadata, and then the client basically can generate a suitable building for this defined space. And what I asked in the beginning for the software was whether it is possible to generate these cityscapes in real time to then be used for games, whether it is actually usable in terms of performance and doable using these open data sets, because for instance the BlackShark.ai model that I previously mentioned, they have access to satellite imagery and much more data which is not publicly available. So it's also a question whether the data is sufficient enough and to generate a somewhat convincing result. And so my solution basically is a real-time game engine world generation, which basically works per chunk, so it divides it in several chunks that are similar to, probably most similar to the chunks that you know from Minecraft or so, that it basically, when you move the camera, it generates new ones and such. And my solution basically takes the data from OpenStreetMap with the HTTP request, downloads it, and then it processes it, and then it tries to display it. So here it basically explains, if we take, for instance, the camera is set here, then the engine will basically trigger the generation of the chunks that are nearby in a certain defined radius. For instance, these have already been loaded, and then if a new chunk has to be loaded, it will basically send the coordinates to a separate thread. This thread will make an HTTP request on the OpenStreetMap data. Then it will download this data, which is in XML format. It will be parsed, which then is stored as data, and this data is then later converted and transformed into the actual render data. So there are the vertices and indices created and the UE coordinates. And this renderable data is then added back into the engine. And for each chunk, basically, it's done on a separate thread for performance reasons mostly. And I evaluated this on consumer hardware on a AMD Ryzen 8700G, so a somewhat recent CPU. And I basically only render a part of the scene, so if chunk is too far away, it will get removed at runtime, because otherwise it would, when you move around, it would just generate too much and would basically crash the system. And I measured here how long it takes to generate a chunk with a chunk size of 50 times 50 meters, 100 times 140, and 250 times 250. And it basically shows also the distribution that is actually very performant, so it only takes about half a second for 140 times 140 meters. And you can see in the graph that it also varies a bit, because some chunks are basically empty, and then it will not generate any buildings, and then it's quite fast. And some take quite long and have complex geometry, as you can see, up to 3 seconds about. So most cases are actually very fast. So currently I have a prototype implemented, and it still needs some more improvements. For instance, the performance is okay for most parts, but not really very great. So it probably needs some LD or other things. And generally speaking, the system is basically very expandable. So currently it renders buildings, streets, trees, train tracks and such, but there's always room for improvement. And this then could be used to implement a sample game. For instance, one could implement a game where you drive on the real roads, or you could implement a flight simulator, something similar. And yeah, so I have some screenshots because last week a famous game basically released the power up, and I thought it would be quite interesting to have it here too. So these are real screenshots, and now here I have a demo how it works. So here we can see that the camera can be moved freely around, and new chunks are generated as you move. The buildings basically are generated with some random textures that are assigned to them and random windows, but the map data is real for this. So it also distinguishes between flat roofs and non-flat roofs. And basically, there's a geometric library which can generate the center line for a roof, and then it basically connects them. And yes, this was recorded on my desktop machine, so it's rather performant, I would say. It's full filament, because I wanted to try the engine. So and the trees are rendered instant, so it's just one GLTF object that is basically placed in different places. For instance, if the chunk cannot be loaded because the OpenStreetMap server has a limit to it, it will basically mark the chunk as not loaded, and then it will try to load it later. And yeah, that's basically it. I mean, I could also show it in real time on this machine, but it's a very old laptop, so it's not that powerful. It's 10 years old. So yeah, here I reduced the graphics quality a bit, but it's also somewhat usable, I would say, because it only has 4 gigabytes of RAM. So yeah. And you can see it also removes the old ones and builds in the new ones.
Nice. Okay, thank you. Any questions?
The chunks that are rendered, are they set normally again, or can they be dynamic as well? So they have the amount of chunks.
Oh, so yes, it's defined at compile time for now, but I think it could be changed at one time. haven't tried it yet.
Is it possible to get like the size of the chunk, so to estimate how much data is in one chunk beforehand, so you could like scale the chunk size based on the data amount?
Haven't tried that yet. I mean, yeah, because it would have to make the call to the HTTP server from the OpenStreetMap every time again.
Yeah.
Because it's basically calls with these are the boundaries, and I want to have the data that's in these boundaries, and it would probably be too much overhead. So, yeah.
Okay, thanks. Next one, please.
Hello, my name is Jan Messner, and today I'd like to present you my bachelor thesis, a 3D trial bike simulation. My project extends a previously developed 2D trial bike game by Stasha Tadic into a 3D environment. And while the original game focused primarily on suspension dynamics, the transition to 3D enabled the implementation of more advanced vehicle dynamics, including a Pazeka tire model based on the magic formula. In addition, the project introduces a large-scale 3D map and ragdoll-based character mechanics to enhance realism in gameplay. The project builds upon extensive existing research in vehicle dynamics, motorcycle handling, and tire modeling. For this project, I mainly relied on the work of Hans Pazeka and his research on tire dynamics, especially the Pazeka magic formula that is used in my simulation. Vittore Cosaltea's work on motorcycle dynamics is also a key reference, and particularly his work on two-wheeled vehicle behavior, stability, and handling characteristics. Existing research provides detailed models for motorcycle and tire dynamics, but it's less clear how well these models can be approximated in real-time engines, such as the Vienna physics engine. And this led to the following research questions of how well can one approximate perceived realistic motorcycle handling using rigid body simulation, and how does the tire model influence the perceived maneuverability of a motorcycle. And based on these questions, the following hypotheses are formulated. A rigid body physics model can approximate the geometry and perceived dynamic handling of a real motorcycle without visual jitter, and implementing a Pazeka tire model will increase the perceived realism of motorcycle maneuverability and improve subjective rider experience. So to achieve this, I first had to find a suitable model for the bike that is preferably free to use, and to make it usable in the engine, I then had to prepare it in Blender by cutting it into pieces of chassis, handlebars, suspension parts, and wheels, and then reassemble it in the engine. And the same is also true for the rider, where pre-modeled and the pre-rigged character was cut into pieces and reassembled using joints and constraints. Similar to the previous work, the front suspension was modeled using a slider joint, and addition swing arm style rear suspension was modeled using a hinge joint. And both are then controlled via a proportional derivative controller to simulate the suspension using the spring damper law. The motorcycle can be controlled using throttle steering and independent front and rear brakes, similar to a real motorcycle. And to improve usability, the game is designed to be operated with a standard Xbox game controller. Because motorcycles are inherently unstable, several 3D controller-based assistance systems are implemented. Steering assistance combines user input with a controller that adjusts the steering angle based on the motorcycle's lean and speed, and another controller generates the roll torque to achieve the desired lean angle specified by the rider. Additional stabilization systems allow the rider to influence the bike's forward and backward pitch, as well as another system to help align the motorcycle with its direction of travel while it's fully airborne, resulting in more predictable jumps and landings, so you don't land on an angle. Propulsion is generated by applying torque to the rear wheel through a motorized hinge joint, and the motorcycle uses an automatic 4-speed transmission that shifts gears based on vehicle speed and apply stored according to the current gear and throttle input. The tires are a critical component of the motorcycle simulation, as with other tire model, tire forces are usually approximated using simple friction coefficients. The Bazeka model allows force generation to vary with wheel slip and producing more realistic acceleration, braking and cornering. The model describes the relationship between the slip angle alpha and the slip ratio kappa and the resulting longitudinal and lateral tire forces, which are computed from the relative velocity between the tire and the ground, as well as the rotational speed of the wheel. The slip angle and slip ratios are then used together as inputs with the Bazeka coefficients, which describe the tire stiffness, peak force, and the shape of the tire in the magic formula. And that computes the longitudinal and lateral forces. The resulting forces are then clamped by a friction circle, which limits the combined longitudinal and lateral forces to be within the circle defined by the friction coefficients of the tire. The forces are then converted to impulses scaled by time step and applied to the tires. To test the bike's handling and maneuverability, a 3D map was generated using TXA landscapes in Blender, which is a fork of ANT landscapes that also has automatic texture generation. With the tool, you can randomly generate various terrain types using different noise functions, and the generated terrain is then rendered out as a height map and loaded into the engine, where the ground test function was modified to read out the height map data, interpolate it, and use that value as the ground height and the surface normal. To evaluate the simulation, a user study with 12 participants was conducted, and the questionnaire was divided into 4 categories, namely background information, perceived realism, controls, and visual cohesion. Overall, 144 responses were collected, of which 86% indicated agreement with the positive statements about the simulation, and a one-sided binomial test indicated that the proportion of agreement was significantly higher than 50%, suggesting a statistically significant majority of positive responses. While the results were generally positive, some weaker areas were identified. Several participants reported that the motorcycle speed and weight did not feel fully realistic, and a similar number found the bike difficult to maneuver in the terrain. Those are the questions B1 and C2. And the reported difficulty of maneuvering the motorcycle through the terrain was also reflected in player performance, where a third could not complete the level. But completion rates differed by experience level, with 75% of gamers finishing the level compared to 50% of non-gamers, suggesting that the level difficulty was higher than intended. Overall, this project demonstrates that a motorcycle simulation based on rigid body physics can produce stable and believable handling characteristics in a real-time environment, and the implementation of Bazeka-based tire model contributed to realistic and responsive motorcycle handling, particularly in cornering and traction. The user study results indicate overall positive feedback regarding realism, with statistically significant agreement across responses. However, limitations were identified with the perceived speed, the level difficulty, and maneuverability on the rough terrain, suggesting areas for further tuning. Overall, the simulation achieves its goal of creating a physically grounded motorcycle experience while highlighting the trade-offs between realism and playability in a real-time vehicle simulation. Thank you for your attention. Any questions?
I would have a question. How many of the, do you know if some of the people taking part in the user study had experience with concretely motorcycle games, or were motorcycle riders themselves?
Yes, I've also asked for that. There were some, not too many, about a third of the people had some, but no real experts at the end of the day. It were more like people who had a bike when they were younger, like a motorcycle. Mm-hmm. And they did, I did look at it, and they did have a lower mean score in the questionnaire, but not by too much.
Mm-hmm.
Do you have some sort of video or demo that you can show?
I have a video, but my computer is not too good, and usually struggles with an empty void. Yes. It's a bit dark. Yeah, you basically just have to get to the top of the mountain where there's a flag, and yeah, the difficulty was mainly coming from the bike constantly flipping back, because it's a bit of parameter tuning, because I kind of wanted to make it hard and I didn't want to make it too easy, and wanted that people would fail. But this video is also not the last version of it. There was still some improvements. Yeah. Yeah. But it's cool because the whole terrain, everything was generated algorithmically and textured and everything.
So you simulated speed by applying torque to the rear wheel. Is there any, I guess, simulation of the rider like leaning more forward to compensate for increased speed, or how is that handled?
It's more just forces being applied to the chassis to move it forward and backwards, but no, there is no assistance if you heavily go on the throttle,
Mm-hmm.
you will do a wheelie.
Okay.
Yeah. And when your head hits the ground, it releases.
Thank you. Next.
Sorry, can't use this one.
No, I just put that.
So good morning everyone, my name is Prof, and today I'm gonna talk about my master seminar related project, which is AI assisted game engine for prompt development. So the core idea here is simple, that instead of writing handwritten code, we just use the LLMs that are available. For here I use the cloud and the local LLM. And also I extended it to the 3 different real-time multiplayer interaction. So large language models are like becoming generally used across the software developments, because they can generate and modify the code from the plain text, and it can create like rapid prototypes, which you just describe your ideas and it's just generate the code. So that applies to my game development, and the reason I choose game, those games are usually very hard test bed. Like game must handle many things at the same time, like handle user interaction like visual updates or rule handlings or state management. And also the code must behave like correctly, not just look correct. And also I extended it with the multiplayer. In multiplayer chess, the player is separate. Browser must share same state of both
the two players must share same board state, the difficulty levels and the move history in real time across the separate browser. So as proof of concept, I created a multiplayer chess games which consist of AI-assisted gameplay and different multiple difficulty levels and real-time synchronizations with generated through end-to-end forms. So the related works fall in three different areas. And the first one is like the LLM code generation. So I used it to create the entire games through the commercial model which is available, and that's clouds on it. And also I tried with the open coding model which is like Quinn 2.5, and I used the university provided DJX Spark, and I connected with the WebGPU API with my VS Code agent extension which is continuous, but that's local. I still on working with that. And also I tried with real-time web communication, the third one, and I tried three different models. One is like metrics, which is like decentralized, and the other one is like the WebSocket, which is like server relay, and it's like centralized. And the other one is like the WebRTC channel, data channel, which is like a peer-to-peer messaging system. So the key observation over here that all these ideas already exist, but it never combined together. Like people study them separately. Like for example, AI code papers stop at like a single player game. It never continues with the multiplayer. And also the networking paper also usually use code that are written by hand. So I came here with almost to put all them together in one AI made like multiplayer games. So that brings me to the research gaps. Three things are missing current practices. Like the first one, that LLM generated games almost and always remain like statics, like a single player prototypes, not with multiplayer, and they are not also extended to the networked or like interactive system. And the second is there is no controlled comparison how different this multiplayer synchronization architecture are for the generated games. And the third one is like all these prompts are there, but it's rarely reproducible. Like it's never stored as a data to reuse by maybe another person. So that comes to the research question for me, like can LLM generate a complete playable multiplayer game through an interactive prompting, and how do the decentralized and centralized and peer-to-peer synchronization layers compare when you attach it all together to it? So I compared them with the speed and the stability and the implementation, how hard was it? And the main point is that all these stand with the same generated code. Only the connections are like changing. So the tests are like fire. So the solution follows here. The primary setup follow the client-server architecture, where the user write a natural prompt, and the Flask gonna forward the Flask from the backend forward that to the cloud API, and then the generated code is stored as a JSON artifact. The game itself run inside an isolated iframe in a React front end. So before loading the before it's load, they verify the runtime variable, the player number, the difficulty level, and which mode they are choosing, like the transport mode, etc. And also the chess game that took me like almost 17 prompts to create like a final multiplayer chessboard game. And yeah, the multiplayer synchronization level where the main engineering is contributed, like the generated chess game never talk directly to the networks. When a player makes a move inside the iframe, it goes to the backend parent React application using a post message, and then comes the parent forward it through the networking layer which they choose, and then it and then the the parent forward it through whichever network is selected, and on the opponent side the event is injected back into the iframe. So I tried with 3 different multiplayer, which is metrics, and which store the moves as a room event, and but it's required like pooling before any updates is done. And then when it comes to the WebSocket, which I connected with the Flask socket IO, and so that's why the moves you can see instantly. And then comes to the web RTC, which is like a peer-to-peer messaging system. So it's a bit complicated to set up, but yeah, it's much more okay. So I evaluated all this by adding a timestamps to every move and measured the delays until the opponent get it. So as you can see from the table, the matrix is having highest latency. It's because of the implementation, how we done the. But the lowest real time you can see from the WebSockets. Yeah. So the conclusions goes. That an LLM can generate a complete playable multiplayer chess games. For me, it took like 17 iterative prompts, and also it's connect around all the multiplayer, which is like metrics or WebSocket or WebRTC. They're all connected together with the same generated code. Yeah, thank you.
Any questions?
Should I show?
Hi and good morning. My name is Helmut, and my bachelor thesis is on neural rendering for subsurface scattering. The goal is to approximate the transmission part of a real-time rendering solution for subsurface scattering and see whether a neural shader can improve upon the performance while still keeping the visual fidelity. And furthermore, to see how different feature sets, network architectures, and so on factor into these results. How I did that was I've expanded upon an existing renderer, added a data collection pipeline to it, trained a neural network, and implemented an inference as an alternative to the analytic render part. And then I evaluated what came out of that. So first of all, what is subsurface scattering? It's basically light transport inside objects, which is especially necessary when trying to render translucent material or slightly translucent, like skin, foliage, marble, or wax. And there have been first attempts to implement it for offline path tracers, basically by substituting a diffusion profile BIDF with especially BRSSDF distribution function, which can evaluate the scattering term, and then there were also attempts and solutions for real-time. My thesis is built upon a very contemporary solution which was presented last year at the SIGGRAPH conference by Chang and Dion, and they've implemented that in the NVIDIA character renderer, which is also open source on GitHub. The other part is neural rendering, that is rendering based on neural networks, that is multi-layered perceptrons as envisioned in the 50s, and especially the ability of neural networks to approximate mathematical functions arbitrarily well. In rendering, this was used most prominently in upscaling and denoising at first, and in recent times more and more parts of the render pipeline have been substituted by neural network-based solutions, be it neural shaders, neural materials, or neural textures. More concretely, the NVIDIA RTX character renderer, as you see on the right side, is using an implementation which you see parts of the left side, which combines two different ideas. One is a diffusion profile, and one is a ray trace component. And this ray trace component itself is split into two parts. So once they try to evaluate the ray which enters the volume as if there were no scattering, which they call a boundary term, which if you would think of the TO exits just directly. And the other part is sampling different scatterings across the path, and this second part, so to say, is what I try to approximate. So only the integrated scattering part I try to substitute. How I did that, I built a feature set based on what I've seen the actual function is working on, like material components, volume geometry, ray tracing geometry, but then in a suitable form for neural networks, for example, taking logarithm to hold the variance in check, or taking the dot product of two vectors so that you just store one float instead of two vectors, and also in a way which is also guiding analytic solutions. And then I built a data pipeline in the renderer, which is built upon the NVIDIA rendering hardware interface, and yeah, basically collecting the data and writing it into a CSV file. And then outside of the renderer in Python, I could load the CSV file in a Python notebook, and with like most standard ways, libraries, PyTorch, I trained two different neural networks, one smaller with 2 hidden layers, each 64 neurons, and one larger one with 3 hidden layers, 128, with different sample sizes using atom optimizer, mean squared loss as loss function, and available activation function, which is all nothing fancy. And then I reconstructed the neural network in HLSL. That's what Ray Tracer uses, and renderer uses, and stored the weights which I've exported from Python into simple C++ arrays. And then I extended upon the UI to switch between the neural path and the analytic path, and also between different network architectures to compare what I've built. And now it's for evaluation, and I'm not sure whether one sees much, but on the far left you see the part without any transmission, and the one next to it is the analytic solution, like the original implementation of the renderer, and then different neural approaches. The first one, it's darker, and what you can't see here in the screenshot is the first write was very unstable, and had a lot of artifacts removing the lights. So this didn't work out, so I trained a larger network, which I thought worked out pretty nice. In direct comparison, it was a bit overshooting, it's a bit brighter than it should be, but worse is the problem that it took much more time. It took like twice the time to render it with this large neural network. So I tried going back to the small one and just feeding it more data, like tripling the size to 10 million samples, and that actually worked out very well. I mean, in the same way as the large one, that it's also a bit too bright. And just 2 days ago, I trained just for more samples to it, and now I'm very close to the analytic solution, which if you compare like the last one on the right with the second on the left, no? And I mean, I don't know whether one can see it here that well. So conclusion is, there is performance to be gained by substituting the analytic part with a neural renderer, even if it's only 10% or 9%, by still keeping visual fidelity. And as I said, the larger network was more apt initially, but then lacked in performance, while the most successful solution was just to increase sample size. Further optimizations are possible, of course, like more sophisticated feature sets, or actually perhaps a reduced feature set, because there's a lot of actually redundant information, like storing the thickness and the logarithmic thickness, and perhaps a neural network can learn that what is important by itself. This would be especially good for attention networks, which might be but also a bit too much perhaps for this question, but actually to that it learns which parts really were important for coming up with the solution necessary. And then one could extend upon like the whole subsurface scattering solution, not only like the integrated part of the ray trace part, but like also the diffusion profile. And one large question would be how this could be adapted to other models, to other scenes, to dynamic scenes, because I mean it's real time, but it's still a static scene, which I've trained on. And yeah, I mean the last remark is, I'm not sure whether I'm mistaken, but it's a different approach than what is generative AI doing, like taking samples and trying to fit labels, let's say, where LLMs often have to fit in or are built into, so to say. But this is more like not substituting classical rendering, but coming up with a different way of processing the same function, so to say. And I didn't prepare actually, but now that everybody showed something, I also want to show that the live demo.
Hello everyone, my name is Helmut, and my topic is my topic is accessifying web pages. So it is basically, my goal is to create a WordPress plugin prototype for media accessibility. The goal is to help the authors, content authors, who upload images and videos and audio and any sort of media into the WordPress. It's to help them generate alt text. For instance, for images, alt text, and for audio to extract the audio, to make a transcript, and for video, captions on the without leaving the website itself. So the current prototype uses models I use local models without paying for them. So they are run through the DJX hosted endpoints. So the media is processed through our own setup instead of paying for an API service. So next is so the motivation is that the accessibility, media accessibility in general, it depends on the authors to remember to add the metadata on most websites, on like high-end websites, of course, because they are like well paid, or because they are like it's part of the job description. Maybe they do it by themselves, or they automate it. But on most websites that use WordPress, it isn't the case. Like for a low-end company, for instance, you do not see captions for videos. You don't see alt text for any image, and like it becomes a problem for anyone who is using screen reader, or anyone who like is development, like they are using they are like not well in terms of hearing or sight. So images need alt text. Audio and video need captions or transcripts, obviously. The media becomes less accessible for the users who, like I said, depend on screen readers, or those who need captions, those who can't really hear well but can see well. So for videos, they would have captions. The plugin idea, of course, is simple. It's just to detect like all the media on the website, to generate a draft with the local models. It's basically a draft. It's not really perfect, because of course you cannot entirely depend on AI models yet. At least not the free models, because they do make some mistakes. And it is you get the draft and you save it back into WordPress for the review of the author, so that they can either take it as it is if there is no problem, or make any changes, or not use it at all. So the screenshot here is the WordPress admin area, where you can right now it's just for images and for video, and the second one is just like a demo. It's not really it was just a testing phase. Okay, so yeah, so the need for this accessibility obviously comes from this this need for like I said, needing this thing, needing this captions or alt text from images, and then related work. So instead of treating each paper separately, I grouped them into 4 sections, 4 areas. So the first section is standards and web accessibility. So these they define the accessibility need, and tell us, show us how to issues like missing alt text, and how they are affecting users the users. And the second is image accessibility and alt text. This includes earlier systems Web Insight, Facebook automatic alt text. If you go to Facebook, the alt text there is pretty decent, but that's because it's Facebook and not WordPress. And the newer vision language models like Lava and Blip. Lava is the one that I use for my image alt text generation. And the third section is speech to text and captions. So these studies, they show that Whisper is relevant for transcription, but the captioning studies also are important, because they show that automatic captions can help, but there are errors. So these errors make it so that the author who has to review this text, he is not, sometimes he doesn't understand it, because it makes errors. And the final point is CMS and tool support, of course. It's important because it's not just about these show that it's not about just generating text, but also making sure that it's all saved inside one workflow, instead of like doing it separately. And the research gap. Okay, so okay. So from the related work, the gap is that, like I said, in most tools, it often stops at detection, while on the other side, of course, the model papers, they show the descriptions or transcripts can be generated, but they often stop at the model output, so it's not. So the question we ask is, how can the WordPress plugin use local models to help authors create reviewable accessibility metadata for images, audio, and video? And the image shows like the generated captions for video and for audio as well. And like you will see later when I show the demonstration, but most of it is right, but it did make like small mistakes, as you can see in the generated the block. I've been carrying my hair, it says, instead of I've been cutting my hair. So yeah, it obviously makes mistakes, and if the other doesn't check, then that's just bad. So, and the workflow that I'm aiming for with this is to first detect the problem, detect what's missing, and to generate, and then send it to the author to review, and then they decide whether they can use it or not. Okay, so this is the proposed solution architecture. It's that the WordPress plugin is kept as the author interface. The plugin first scans the media library and then sends media files to small fast API services, which are running on DJX Spark, which you can get from the beginning. Then I implemented two main endpoints, which is the caption endpoint is used for images, and the transcribe is used for audio and video to transcribe them. And for images, the backend uses Lava to generate an image description, and the plugin saves that result into the provided. The WordPress provides a default alt text category, this plugin saves the generated alt text into that, and which the author can review and either delete or change it. And for audio and video, the backend uses Faster Whisper, which can also be used at scale, unlike Lava, which has some restrictions, I guess, with licensing. So this returns a transcript and timestamp segments. The plugin then saves the transcript and generates a web caption file. And for videos, it also creates a shortcode that can display the video with captions within the website. So the point is that it is self-hosted instead of paying for anything. So okay, this is the current prototype. So you just first scan, for images, you click on the button, as you can see here. You first scan the media images, and then the third option, which is scan and generate with AI, and the last option is for audio and video. So right now, like I said, it scans the audio and video, sends them to DGX, and then the endpoints, and then receives the transcript, and it generates a VTT caption file. The second screenshot, as you can see, shows on the right, it shows that whatever is generated, it's also saved within the box that comes by default. Okay. Then the evaluation plan. Since this isn't just a model experiment, we want to evaluate it as a tool that also supports the author. So we ask these questions. Evaluate it did we find the right media and say the right fields, and for quality, to check the quality of the captions that are generated, and and for the workflow to see how it actually helps the author. And of course, finally, trust and review, where the author needs a proof. Yes, and there is also like a limitation, like I said, which is that you cannot entirely depend on AI captions, like these local models, because they're not good yet. They're decent, but they're not like the paid API ones. And finally, this is the conclusion, which is that current prototype works. The images are generated and they're saved into the WordPress alt field. For the audio and video transcripts and VTT files are generated. You can also download the VTT files and correct them if you need to. And the caption video shortcuts are generated. And the next step would be to like clean the UI and for flow, evaluate the quality, and to extend towards video descriptions, plan the deployment, plan how we can deploy it, and test with WordPress users to see how it actually works. And the main takeaway is that the project moves from checking for accessibility problems towards helping others fix them inside CMS, and I will now show you the demo.
Can you narrate the demo?
Hmm?
Can you narrate it?
Yeah, of course. As you can see, this is the like the settings page of the like plugin, and first I'm scanning the like the images. You can see like I uploaded 5 images. I only set it to 5 so that like it's faster. And then I generated like first I only generate the images with the DGX. Takes a minute. Seconds. You can see like the alt text is generated, and there's also
And that was entirely on the local NVIDIA
Yes,
DGX
yes.
part, right?
on the DGX part.
Mm.
Let's see. Let's refresh this. The captions are like they're not wrong, but they're not exactly accurate. So my goal is to find a model that is closer to like the paid models. And now I will show you the captions for the video and the audio files, the transcript, and for the video captions. This is the video, and as you can see, like I made a mistake, like I said before. Instead of cutting, it says, and this is the shortcode that automatically, instead of copying the links manually, you can just, and as you can see, like once you create a page for this, you can see that the caption, like the video, for instance. The video will show captions, like the same.
I've been carrying my app for about 9 years at this point. And even if this channel is not about learning new skills, I feel like this could be a really valuable skill to teach, especially right now. So in order to
The
start
background noise
with,
is like
first,
one of my
I heard
like,
you can find one of the ones on Amazon. I'm using this one. It costs $40. It works pretty well. The hair clipper needs to have
yes, that's it. Thank you.
Okay, any questions? So maybe for the rest of the work, you should include also a full-blown paid
Yes.
AI because of the quality issues.
Yes.
or at least find an open source one that doesn't have any quality issues.
I did try OpenAI's,
Mhm.
and it worked really well. And it was like
Yeah.
very descriptive, but like it's expensive stuff. So
So maybe you can, you should include it at least as an option
yes,
for people,
of
you know.
course.
Okay, I will present my thesis, which is the Vienna Game Geometry Library. It's a design and implementation of a collision detection system made for games, and it is clearly part of the, hopefully, the Vienna repository suite, which is on Professor Hlavacs' GitHub repository. I don't think I have to explain this topic very much. I think all of you know it, and we've heard some topics on this already. So the basics are that games need to know if objects are intersecting, and it's probably, I'd say, most games need some kind of collision detection. Even 2D games can be naive or whatever. And there is a difference between collision detection and collision response. Collision detection is what this library focuses on, which just handles the detection if objects are colliding and how they are colliding. And collision response would be like the Vienna physics engine, for example, does. It reacts to those collisions as well. So the Vienna Game Geometry Library is a focused C++ library just for collision detection. Some related work, other projects that cover collision detection, of course the physics engine and some commercial engines. I think some of them you might know already. Bullet, FCL, which is fast collision library. This is a little bit more unknown, but it's for robotics. Jolt and React Physics 3D, with React Physics 3D being a general rigid body physics engine, and Jolt in this case is a bit more fitting because it was also made for games specifically. Jolt was started as a hobby project by a developer of Guerrilla Games, which made the Horizon Zero Dawn and Horizon Forbidden West games, if you know them. And it evolved to a full-blown physics engine they use in-house now instead of some commercial. And this is interesting because I think it shows that the general physics engines are good, which are provided by companies, but games always have some specific use cases, and a specialized physics engine or collision detection system which handles just the needs of the game efficiently is always better. And just to cover some algorithms which pertain to this topic, GJK obviously, which is very old now, but still used because it's very good. SAT, separating axis theorem, which tests whether there is whether two objects can be separated by an axis, and EPA. So EPA is mostly used in combination with GJK. GJK is, it builds a simplex and tries to, there are some variations, but so you can calculate the distance or just use it as a Boolean intersection test if they are intersecting and the EPA, which stands for expanding polytope algorithm, is used further then to build on that and builds the contact information. So this brings me to my research gap and question. The Vienna game geometry library uses projective geometric algebra and conformal geometric algebra. I won't go that deep into this because it's a very complex topic, but basically it's a mathematical model to describe geometric primitives. It builds upon the homogeneous coordinates, which is part of that, but homogeneous coordinates alone is actually an incomplete model, basically, which you're familiar with. So it builds on that. PGA is fourth dimension, like homogeneous in CGA, which includes round objects, goes into the fifth dimension. So the research very few libraries use this, or I have not seen any library actually that uses this, except for one library, the C4 engine, which the author is a very prominent figure in the geometric algebra space and developed a mathematical model. So what are required features and functions of a game geometry library is the research question, and the hypothesis is what it minimum needs collision detection between primitive shapes, some spatial acceleration because of the real-time use, and ray clustering to be useful for this. The library currently supports for primitives, which are axis-aligned blocks, a capsule, a polytope, which can be any set of points, and a sphere. And the library basically is heavily templated, so you can create a system like this you can see here on the bottom right with this, and you specify the broad face, because the library currently supports 4 broad faces, BVH, sweep and clone, and index grid being the wider ones. I also have a brute face, a brute force broad face, which was initially just used to test the bounding volumes, but I've kept it in. And it was also useful for comparing. With BVH and brute force, you can specify the bounding volume. If you leave it empty, like here in the example, it will default to AABD, axis-aligned bounding blocks, which is currently the only bounding volume supported. And sweep and clone obviously doesn't need a parameter, and index grid you can set the size. On the top you can see the API functions for creating objects in the library. You define the primitives with the define functions and get back a geometry handle, and you use this geometry handle then to instance or add this geometry with initially with just a position, but you can scale, translate, and rotate it later as well, and I will come to the difference between geometry and instance handle. Basically, a geometry handle is, and the separation is there because then you can define a shape and reuse the definition, the local definition, of course, and instances multiple times. Now coming to the collision results which the library offers. There are 4 functions which the library call. Everything happens through the collision system, which also has these defined functions, and you can query all objects which will return a vector of all collision pairs, which you can see on the left the structs which are returned to the user. So a collision pair is just two instance handles of the objects that collided and the contact manifold, and inside that contact manifold is the normal vector, which is and the depth, which combined tells the user how to separate those objects. So if you go along the normal vector multiplied by the depth, you would separate the objects exactly. And you also get the two witness points, which are basically just the two furthest points into the other objects. So, or in other words, the point on each shape respectively which first touched the other object. And you can also query just two objects instead of querying all collisions, and you get the full contact manifold, or you can also just do a Boolean test which doesn't do the contact manifold at all and just returns if there's a collision or not. And there's also a array cast function which returns a vector of ray hits, and the ray hits just every shape hit with the information again, position, normal, and the distance along the ray where it intersected the first object, and they are ordered by the distance. So this was the collision system part which the user sees. This is all in a top namespace called VGeo, and everything else is in the internal namespace, so the user shouldn't really interact with it. And the whole backend is using templates and concepts, because extensibility was an important feature for the library. So on the right you can see a C++ concept, which is basically just like an interface in Java, which you probably know. And this defines what, in this case, a bounding volume, what functions does it have to provide to work. So if one were to extend, or if one wanted to extend the library in the bounding volume, they would just have to anywhere in the code base add a class which implements those functions, and the creation should automatically work through templates. Of course, the library only supports convex collision detection, so any geometry loaded in by the polytope gets converted to a convex hull by a quick hull, which you can see in the top right, and how the model is converted. The library also supports a pair cache, so it caches every collision and flags instances as clean or dirty, and if both are clean, it reuses the result. And a quick mention about the handles as well. The handles are just 64-bit types which encode some information. The geometry handle uses the first 32 bits for index and the other bits for generation, which is used just for a slot map in the backend. So, and it also encodes the type. At the bottom I have an example how it could look like. So this would be shape type 3, generation 1 and index 5. The index just encodes where in the slot map the shape lives, which is just a string factor. Okay. And now coming to the evaluation, how I tested it. First, I answered the research question, which features a library like this should contain. I surveyed some collision detection systems of physics engines. Most software in this field is a full-fledged physics engine. Very few only separate the collision detection and don't do collision response. But of course, everyone supports normal collision detection. Everyone supports spatial acceleration, which is broad faces. And but only not all of them support raycasting, which does make sense for some which are not used in games, but I found it's not strictly necessary to have them, but it is useful for games. So the Vienna physics engine doesn't support it, but it supports some kind of object detection in a direction I saw, which could be replaced by a raycasting API. On the bottom, I tested the API functions, and you can see the broad faces I used. I tested it with up to 10,000 pairs, and for the add, you can see that brute force and the bounding volume hierarchy are identical and the fastest. This is because bounding volume hierarchy only yields after the query, and this is the cheapest to insert. And index quit and sweep and prune are a bit more expensive to insert because you have to do the full insertion logic every time. Query all. The bounding volume hierarchy was the fastest in the testing I did, and brute force being a magnitude worse than all of the others. And cast array was not very efficient for the bounding volume hierarchy, which is expected because of the structure. It has to go through the whole tree, whereas for sweep and prune, for example, it's very simple to do some select tests with array. So this suggests that it really depends on what the use case is for the game, what is you have to do. This is the collide. The collision in the game is done via the visit pattern from C++. So there is a GJK plus EPA fallback or general case, I would say, which works for every shape and is the least efficient. And then the specialized collide function on top, namely sphere, capsule, capsule, and the bottom two use the fallback function. And as you can see, I tested the polytope. The bottom one is to improve those T-plots, convex hulls, which is by far the most expensive. I tested 5,000 shapes and took the mean to test how fast one is. And on the right you can see also the cache, which was also tested with the same data set, how efficient it is when the results get reused. Thank you.
Can you go back to the adding to sweep and prune? How do you add objects to sweep and prune?
I go into the
Because things have to be sorted along an axis,
yeah.
right? And here's the crux. If it's just an array, you have to move the array. If you insert something. If it's a sorted list, you
No, it's-
add one item.
No, I add just one item,
Mm-hmm.
and it's. I'm not sure actually.
So you have to find things are sorted along an axis, right? You
Yeah,
have
they are
to- you have to-
sorted along three axes, and if I insert.
Usually your one axis is enough, but you can keep different axes also. But
I use all three axes.
you use all three axes. Mm-hmm. And why do you use that?
Because the adding is less efficient, but I found that I think the querying is
Usually with sweep and prune you have one axis
yeah.
where you have the maximum variation.
Yeah.
And then if you find that there's another axis which has more variation, then you would create that in one step, but don't keep all of the axes sorted. Just pick one.
I have to admit, for the sweep and prune, it was the first one.
Okay,
I added.
yeah.
It was,
So maybe
I could
because
do
going up like this, it's probably it's not really necessary to.
it. Okay, I have to look at it. Yeah.
Yeah.
Mm.
We can talk about it. If it's a sorted list of one axis, then inserting something should be really quick.
Yeah. Okay.
Okay.
Yeah,
Okay.
you're right. It should be actually.
Yeah, but we can talk about the implementation details. Okay. Any more? Do you have a demo or something that you can show us?
I don't, unfortunately, have the project on this laptop. So
Okay.
I thought I don't have the visualization which I did in Aurelia. I don't have it committed. I thought I committed it to the sorry. But it's not that interesting. So here you can see it's just. No, like I only have some moving around of the objects. You can see the orange line is already hit with the arrow. It's basically the demo is probably like this.
Okay, thanks. Move on. Let's move on.
So, hello everyone. My name is Alexander Wolinsky, and today I'd like to present you my Bachelor project called Slang Factory. So, first of all, Slang, it's a modern shader language, and it's good because it's very flexible and suitable for many engines and renderers, so it can provide shaders for different varieties of engines and renderers. And so the main idea of my project is to generate shader code programmatically in C++, then compile it through the compilation API that is provided by the Slang, and then also extract the reflection data, also using an API from Slang, which is called the reflection API. And then basically we can use the generated shaders in an engine or a renderer. So my motivation for this project was that programming a shader often contains a lot of repetitive work, and it has repeated patterns. Like for example, the vertex inputs, the uniforms, varings, fragment outputs, they often follow the similar structures. And also, like the resource handling and shader interfaces can easily become error prone if everything is written manually. So if you do it all the time manually, actually, hard coded. And so I wanted to explore whether the process can be made more modular by generating shader from structured input. Yeah, so we give the structured input to the factory, and then it provides us a valid shader. So yeah, the goal of the project was to build a modular Slang factory. Yes, that provides us shaders. And so the system itself should accept the structured parameters for shader, and then it should generate the valid Slang shader code. Then it should compile it to the compilation API, extract the reflection data, and then also provide a fully compiled shader so the renderer can render it or engine can use it, etc. Why I decided to use Slang one more time? Yeah, because so Slang, it's actually it was kind of scary to use Slang, I would say, because Slang is a modern language, and there are not a lot of information about Slang. Even if you research for some papers, there are 5 papers in the internet about Slang. So it's very modern language, but it has very good APIs, as I've said. So there is a compilation API for shader compilation, and there is a reflection API that helps you to get some reflection data if you need it from a shader. And that's basically a perfect fit for my project, yeah, because I can generate a Slang code. So I can provide the code, and then I already have a solution. I have an API for compilation of a shader, and I also have an ready API for extracting the reflection data. So Slang is a perfect fit for idea like that. So for a factory that should generate some shaders. And yeah, so now I'd like to talk a bit about the high-level architecture of my project. I won't go into details and tell you how the whole magic works, but just so you have it in your head. So first of all, we have a shader request. So that's basically a class that was developed for shader requesting. So whenever renderer or an engine needs a shader, it can describe which shader it needs exactly. And for that, we have a shader request. So renderer or engine thinks, okay, I need vertex and fragment shader, or I need geometry shader, whatever. Whatever he needs, he just gives it into a shader request. Then the shader request goes into the Slang factory, and that's where the main magic happens. So the Slang factory produces a valid Slang code. So it got the shader request. It says, okay, what I need to make? I need to make vertex fragment shader. Slang factory is okay, provides the Slang code for the vertex fragment shader. Then this generated Slang code that was provided by Slang factory goes into the Slang compiler. Now the Slang compiler uses the compilation API and compiles a shader into any type you need. For example, in my particular case, I'm compiling it into Spear 5 because that's the suitable type for Vulkan, and I work with the Vulkan, but a bit about that a bit later. So Slang compiler compiles the shader. Then we have 2 different classes that work with the reflection API. There is a Slang reflection dumper and the Slang reflection extractor. So first one, the Slang reflection dumper, I made it first. It's basically just for the inspection and debugging. So it just gathers whole reflection data from a shader, and it just dumps it, prints, so you can see it in a console, you can inspect it, do whatever you want with it, and check if everything is going as expected or not. Then, after that, I made the Slang reflection extractor. Now that is something with where we can work with something. So the Slang reflection extractor, it extracts the reflection data and converts it into a C++ structured data. So already an engine or renderer can work with this data, with this structured data, that is provided by the Slang reflection extractor. And then last one is the Slang Shader Builder, and so the Slang Shader Builder is basically a facade class. Yeah, so it just made everything easier. So you don't need to work with Slang Factory, Slang Compile, Slang Reflection Dumper, Extractor by itself. You just have the Slang Shader Builder, so this the facade class, and you can work with it. So this way, it's like it's very modular. Yeah, so you just need the Slang Shader Builder, and that's it. Yeah, and that's the facade class. That's all you need. And also, I wrote there the Vulkan render demo. That's the demo that I've made. So I've created a small Vulkan renderer using the Vulkan guide, and yeah, so this renderer that I made, it can already render the shader that I'm generating with my factory. So exactly. Now a bit more about the current shader generation. So the current shader generation, I only generate vertex and fragment shaders. Yeah, so that's it for now. For now, I just generate the vertex and fragment shaders, but it's already with all different parameters. So you can pass some resource features like model view projection matrix. You can pass different base color, vertex color. Every parameters that you can imagine for vertex fragment shaders are in there. So you can all you can pass these parameters and everything will change. So here the compilation pipeline. So it just a bit more in details about the compilation stage. So after we generated the Slang code, it will be compiled using the compilation API. And so the workflow of the compilation is here. So we create the Slang session, then we load the module from the source string, we find entry points, we program, then we produce the spear file, and then we obtain program layout. It's a bit maybe too technical, but I just left it here. It's also all according to the compilation API documentation. So this whole part of the code was made with the compilation API documentation. Then we obtain the program layout. Program layout is very important for next step for the reflection extraction, because we get the reflection information exactly from the program layout that we got from the compilation from the previous step. And then with the reflection data, you can do whatever you want. So I have a dumper. As I said, you can inspect whole reflection data, watch if something is wrong or everything is good and everything is correct. Or you can just, using the reflection extractor, get the structured C++ data and work with it, arrange and render, etc. And the Vulkan rendered demo. So just for now, this one right here. So as you can see, there is a triangle. So my Vulkan renderer demo is already renders a triangle, and everything you see there, it's not hard coded or handwritten. Yeah, so it was, so this triangle, everything you see there, so the vertex and fragment shader on this triangle, everything was generated purely with the factory. So the renderer that I've made, the Vulkan renderer, just gives the parameters to the factory, then the factory takes the parameter, gets the shader request, magic happens, the shader the shader will be compiled, the reflection data will be extracted. There is also model view projection matrix, base colors, everything you can adjust through the renderer. So you just change the shader request, and everything will be adjusted. So yeah. And that's basically a proof of concept. So with this renderer, we can see that it actually works. We have a triangle, not much, but if you can render one triangle, you can render a million triangles. So yeah. And for now, yeah. So the current limitations. So I intentionally made the limitation that for now I just want to make the vertex and fragment shaders, because there are billions types of shaders. And there are some are more difficult, some are less difficult. It's kind of hard, but yeah. So all in all, I just made a good base for future, because now for the future work, I can add other types of shaders. I can do it pretty much easily because I have, so for now, I have the working end-to-end working prototype. So the whole swap chain is there. I'm generating code, I'm generating shader, I'm compiling it, I'm getting the reflection information, and I render it. I'm able to render this shader that I created. So the whole chain is working. And now for the future work, all I will need to do is just to add other types of shaders. So I don't know, maybe geometry shader will be next or something else, but I will decide it a bit later. And for sure, for as my bachelor project, I also need to write the thesis because right now I just made a lot of cleanup, polishing of my project. I also, yes, well, the conclusion is, as I've said, I have the end-to-end working prototype. I have polished mostly everything. And yeah, so that's basically it. Thank you guys very much for the attention. If you have any questions, you can ask me. For the demo, sorry, I just have this triangle right there as a photo. I gladly could launch my factory, but sadly it's on my computer, and this is not my computer, so.
Do you have images already? Because there's docs images.
Exactly. I have polished up, so here is full README documentation. You can read it. Here's also this triangle. I have the second demo, so this is the renderer demo. I have also other demo that is more interactive. So it's just like a console app, and you can interact. You can create basically. So in this demo, with console app, you act as an engine or renderer. So you decide, okay, I want the position like this, so you give the parameters yourself by your hand, and then the source code will provide it, the Slang code. It's also saved in generated folder. You can watch the Slang code that you generated, and also the shader will be compiled. So if you are really interested, you can visit my GitHub. I have made full guide how to launch both demos. So you can launch renderer demo, you can launch the console app demo. There are only two dependencies. You need Slang SDK, Vulkan SDK. That's it. Only two dependencies. Everything other is.
I think it would make sense to have then more complex demos, more complex meshes and things like that. Yes. Maybe also like something like a shadow map demo. As far as you can get actually, but just one more step in the complexity of the
demos.
Yes.
Okay. Yes.
And that would be very helpful. Okay, thank you very much. So now we will provide you with a stool because there are stools.
Can you share it with?
Or can you maybe just
Yes.
Okay, let's move on.
Can I see the Discord?
My name is Vulkan, and I call my project The Last Fleet, which is a virtual reality real-time strategy video game to investigate the benefits of free roam movement on presence. At the start, I'll dive into theoretical backgrounds relating to presence, and then at the end, I'll show more details regarding the project itself. First off, virtual reality has a distinct advantage over conventional flat screen experiences. Even if video games lately have grown in realism and quality tremendously these past few years, virtual reality still has the distinct advantage from a technological perspective of being able to fully immerse the player in the virtual world and make them feel like as if they're part of that. But can we really say that immersion equals being part of the world? Well, research says that there's a difference between immersion and what researchers call presence. While immersion is an objective quality of a technology that can be measured and compared, presence is a more subjective and psychological sense of simply being there, being part of the world. As for the research question, I always had the nagging feeling from my virtual reality gaming experiences that some games have an easier time of making me feel like I'm part of the world compared to others. And while I kept playing, I realized that the ones that have an easier time of actually engrossing me are the ones that do not feature artificial locomotion techniques such as joystick movement or teleportation, but translate the player movement inside their own physical space directly in the virtual space. This is done, of course, in a restricted bounds, like you cannot have a big open world and use this, it's pretty complicated. But for example, games like Superhot VR or Underdogs feature very small arenas where the player can just use their existing limited room space. So yeah, I became interested in the topic of comparing whether and how much freedom of movement, like free roam, can increase this sense of presence compared to joystick-enabled movement, which is also my research question. And I presented the concept of a virtual reality real-time strategy game to Professor Hlavacs, and he immediately suggested the newly built mixed reality lab at the TU Wien, which hosts like a big room and has a few distinct subrooms, and yes, I would also hold the user study there. As for related work, I'll present 4 papers which are really foundational to what I am currently working on. The first is a paper from 1996, I think, which compared what the researchers called real walking, which translates to free roam movement, walking in place, which is a form of locomotion where the user stands still and they have to mimic walking by like moving their hands and arms up and down, and also what they called flying along the ground axis using joystick input, which is just basically joystick movement for conventional VR applications. Yes, and they find out that free roam does increase the sense of presence. Another paper a few years later from the same author actually distinguishes between the terms immersion and presence, and then gives more details as to why they should be differentiated. More recent paper also compared the subjective feeling of presence related to free roam or joystick movement in a simple supermarket simulation where the users had to, I think, just pick up like items and put them in a shopping cart. And I also found one paper that compares and analyzes what the VR medium brings and changes to the for real-time strategy games as a whole. And coincidentally, they also created like a spaceship combat game, real-time strategy. Yes, and they just analyzed, like, compared classic real-time strategy games versus what you can achieve in VR. So yeah, the research gap I found is that while there are comparisons between free roam and joystick movement and their analysis on presence, and some also go beyond other locomotion techniques, none of the user studies had a large room at their disposal. For the first paper that I presented from 1996, they divided their space into 2 virtual areas. One which was like a training / I guess getting used to the simulation area, and then only the other, which was also both were 5 by 4 meters, that one was used for the experiment itself. The supermarket simulation only featured 3 by 4 meter area, and the mixed reality lab is perfectly suited for this because it features a large room, roughly 11 by 5 meters in diameter. It's a long rectangular room. This is a schematic of it. A little bit inaccurate because the actual room where I would like actually use for free roam is only roughly like this. So there's on the bottom right, there's 2 big doors that can be closed, which are not present in the schematic. And that's how it looks like in the actual picture, very sterile and also soundproof. Because another feature of the big free roam room is a surround sound system, which can also be used in conjunction with other virtual reality applications. So moving on to my solution, yes, I'm working on a game called The Last Fleet, which is a spaceship combat real-time strategy game in which the player must command the last fleet of humanity's space armada against a powerful alien foe. A rough scenario flow, the rough gameplay works like this. These are still blockouts, so the player must defend the worker drones that are collecting ore from nearby asteroids and delivering them to the player's mothership. Defend them long enough until an undetectable stealth ship is constructed that can then find a weakness in the alien's mothership, because the alien mothership at first is invulnerable, very strong, the player cannot attack it directly, so this stealth ship is essential to find the weakness and then for the player to mount a final assault and defeat the mothership. Orders to players' ships are given by hovering the virtual, like their hand, which is a representation of a virtual controller in the virtual world, hovering them over the ships and then holding down the trigger and moving it to a desired location in real space, which the ships will then pathfind towards that. And both enemy and friendly ships have distinct firing angles. And once they detect a target, they automatically shoot at the appropriate target within their ranges. Yes, and since the playable area in the mixed reality lab will the playable area will encompass the entire audio space of the mixed reality lab, which since it is really rectangular, then the scenario is also built in a rectangular fashion. For example, here is a sketch of the aforementioned scenario where the player's area or base is in green, which will take place in like one end of the area, and the mothership is at the other end of the rectangle. Yes, since it is still in a work in progress, the next steps that I would like to take is add 3D models. Because as you've seen, it was the models were just a blockout, and I have access to a asset pack, which I would pick some ships from the ones available here and use them so that the player actually knows that they're like commanding spaceships. Next is add a few sound effects, also to provide more feedback to the player, like ship thrust, weapon firing, or maybe even ship destruction. These would be also based on how close the player is to the ships. So ships far away would not produce any sound for the player, but they have to be like very close and then like hear them like move around next to their ear. Another cool and in RTS games very often met feature is like radio chatter when selecting units. For example, if the player would order ship to move to a specific location, then a synthesized voice or like voice lines would just say something like "on my way," just to give the player a bit more feedback. And also balancing and testing the different values that the friendly and enemy ships have. For example, movement speed, damage, so that the game actually becomes fun and engaging. And the crucial thing is to test if the proportions that I've built in the virtual world are appropriate for the audio room, for the space where the user study will be held, which will imply that some on-site tests as well. Yes, and then finally holding the user study and writing my bachelor thesis as a conclusion. Yes, in my research I also found further gaps for concretely like this free roam versus joystick movement question. The first one is that none of the experiments used a fictional narrative behind the experiments, behind the applications. All of them were either very dry or realistic, like for example just a supermarket scenario where the users just have to pick up some items, or the one from 1996 had basically like a virtual hole in the ground where the users must avoid. So yes, this could also be like a differentiating gap between like an actual with a lot of story, a lot of background narrative, or just like very also dry as well. Another gap was that all of the applications had very little interactivity with the virtual realm. Both the aforementioned examples only featured picking up a few items and that's it. A real-time strategy game implies that there's a lot of decision making and keeping a lot of variables, being aware of a lot of variables that are happening. And another feature that the Mixed Reality Lab offers in that particular area is a fully surround sound system that is positioned in the walls, because all audio experiments taken to presence only used different software-enabled variations that still were like with different types of headsets on the over-ear or just from the virtual reality headset. The RoomScape spatial audio could allow for one application that just has audio from the headset itself, or the other that has it from the yes. And yeah, that's pretty much it. And if you are interested in taking part in the user study, you can contact me via Discord, and I can also provide some further details regarding that. So yeah, thank you for your attention.
Okay, thanks. Any questions?
Perhaps I find it very interesting to think about immersion and presence, as you call it. And when you talk about spaceships, I thought that's like an ideal thing, because like in the cockpit of a spaceship, you already have like movement limited, so it doesn't feel weird to not be able to run around the rooms, as they know. But then you have this strategy map kind of, and I was wondering whether you really can speak of presence there, because the player avatar is some kind of free-floating existence who gives commands to the ship. So I was wondering how one could perhaps connect that, like having like the player as also a part of the setting, sitting in the spaceship, for example, because otherwise it's like a very abstracted instance.
Yes, I am primarily interested in seeing even if this abstracted instance can induce, and to what degree it induces presence, because then the variables become the completely free roam movement, or if the player is like stationary and has to move with the joystick around. There is another concept related to that called bodily presence, where if the player also has an avatar with them, then they feel like their body is then part of the simulation and not necessarily just like a subjective feeling of just being there. So that's the distinction then that could be made. But I focus only on this, like on this abstract layer.
Thanks.
Okay, yeah, let's move on.
Hello, my name is Sida Kalosi, and today I would like to present you my project. It is a web application for mobile phones which estimates transposes, more specifically Tango, using YOLO machine learning, and it gives feedbacks to user when the move is not correct. It is a continuation of my P2 project, but with certain modification. So this is the content that we will go through. So basically, my main motivation for this project was the fact that I dance tango myself. However, it's not something that we do only to the school. It requires a lot of practice, body awareness, and in order to do that, you also need to practice a lot of time the figures yourself. However, it can be that if you don't have someone to correct you, you learn the figures mistakenly, and then it's very difficult to change to the correct ones. So the main research questions that inspired me, it's like it's beneficial creating a web tango application for beginners when they practice on their own. And the second one, is it beneficial to visualize the skeleton of the users when they upload the videos, and does the skeleton help them understand how to do the movement better? I've related work of the field regarding tango, there wasn't so much. It was in a more broader way, in the sense that there were a lot of existing data set created, but it could be mostly from YouTube or using mock-up data. I did use on my practicum to HTM12 from Voliere and Krieger. However, it did cause some issues when I compared them, since I could not see the mock-up data, and also I couldn't visualize them, and it was in 3D, which means that I didn't always have the right values. Other research did try to make YOLO a bit lighter by optimizing the confidence, and also others showcase that there are a lot of frameworks like YOLO Open Pose which can achieve higher accuracy when detecting the skeleton. Until then it was mostly done with kinetics, which that caused a bit of more high performance. Another related work that did inspire me was a certain researcher used multiple cameras, not so much on the tango, but also to research the environment and to see the body movement of certain users. And in regard of the mechanics of the tango, they were quite, but they were mostly on how to achieve balance, how do we walk faster, and they compared the tango dance based on the simple walk that we will have on the street. And one that I really liked was this one from Laguna. Basically, they did try with kinetics and mock-up data to see how there is this association on the body. And this is something that we do need for tango, because in order to do certain movement, you definitely need to rotate a lot, and especially the upper body. Shoulders mainly, and in order to do that, you do require to know the mechanics, but also to understand that you should not lose the balance, because this association, weight shifting, they always go together, and in order to do that, you definitely need to understand how to maintain your balance. The research gap that I did found, while for example here on this picture, as you see, I don't know if it is visible, but my weight, it's only on the one leg that is behind. Because the first leg, this one here, it's the one that you will need to move. And this is why it helped me, for example, with torsion. I know this because I did it on the class. However, there were not so much documentation, so to say, on how to visualize weight shifting so much. And another point, usually the interpreter, the follower in this case, needs to perform moves based also on the musicality, which means if we have a song that is really fast, the steps need to be smaller, sharper, and more quicker. And if, let's say, a song is quite long and there is more melody, then the movement will be quite more slow. However, it is difficult to depict how quick or slow it's the movement done using those frameworks, because there you need to showcase the mechanic of how it's done and not so much how long does it take. Right, so I use Python and also YOLO. My idea, I created my own dataset having certain videos like Ocho Sagrada Crossing, and I used YOLO, which has the key point to detect on the body. I removed the eyes and the face and the mouth, in general the face, because it is not needed. Usually the face, when you dance tango, it stays stable, but you mostly need to pay attention to the upper body disassociation or to the legs, how the legs move. After I do that, I literally normalize the poses, then I get the motion matrix, and finally I compute the velocity, and then I have a window because we're talking about movement in time. So basically I need to have a sliding window that moves through the window and detect this change. I did use at the beginning one camera, but however the problem with one camera is that when you have a more circular movement, let's say the hero, where you move in literally in 4 places, you start on position A and then you go to B, C and then D, it is very difficult to capture this movement only using one camera. However, you can see here from dataset, like if I stay on the Ocho, for example, I will show you this movement later. If I stay in front of the camera, I can do it very quickly and it has really good result. However, if I do the voleo from one camera, it doesn't have some good, the leg move usually from the back. And from the hero, where I have to move in 4 different places, I only capture with one camera only one part of the move. So in order to achieve that, I put 3 different cameras on my room. I put, let's say, one camera where the TV is, one camera where the window, and one in front, and then I performed all these actions at the same time. And that I did conclude it, like for certain movement, having 3 cameras is the best. This is an example. I only use 2. For example, you can see how I have the 2 cameras facing each other, and one move it's done looking at the camera, and you can see my back where it disassociates, and here where my face is, basically it's the camera that's looking at me and also can find the torsion. If you see this one, like it's quite difficult to visualize the torsion, but my body is not exactly straight, so I need to pivot a bit. And with 2 cameras you can capture that. I had a problem with the 3rd one, so I didn't include it here. I started evaluating a bit the module itself. In order to train my data, my CNN model, I use YOLO 11x, which has a lot of high computation performance, but it gives high accuracy. I did, and as you can see, it takes a while to compute this. However, I decided when I trained the data to sacrifice at least for once the speed, just so I get the duration correctly and how the movement is done. And then I need to check how to optimize it. This one now, it's done on my GPU on my local host, on my PC. However, I do have access on the server. I need to try it on CPU, and also I would like to try it in addition using a mobile phone, so I can have different perspective. Here is an example of how it works. Basically, I did use certain one research paper. It was basically on martial arts. The teacher and the student did do the movement together, but only the student did have mostly the skeleton. I did find that it is quite helpful. It also, for me, it helped me myself to understand better my body position. Because with the skeleton you can see exactly when you are straight, when you are not moving correctly, I can adjust a bit the hand for balance, so I did find it quite good. The only thing that it was quite troubling in certain moves, let's say this move that I show here, it's a voleo, that the leg will need to go up. Because sometimes it is fast and sharp, the program doesn't detect it until the end. It goes until a certain point, but then it loses the contact. So my project is still ongoing. I still have a lot of things to do, but this is so far where I have been. I can show you a demo. So basically, this is my project. I have here like the data set of which I do. Here is, for example, the movement that I do without the skeleton, and here you can see it with the skeleton. As I mentioned, with the skeleton it can be quite a bit more slow, but it also gives quite better understanding. What I want to do next is, right now I can upload one video and the program will find it, but I was thinking that let's say user may want also to have 3 videos that they want to upload, and this is what I'm working now, to have 3 videos and shown below, for example, what I'm doing. So yes, this is from my side. If you have any questions, I'm happy to answer them.
Okay, thanks.
Would a higher frame rate help with faster movements?
I did already skip one, but the thing is that I don't want to skip a lot of frames because then I will not be able to capture the movement, because we're talking about moving in time. So
No, I meant like from the source. If the source video would have a lot of frames that can be analyzed, if that could help with analyzing faster movements because the program has more to work with.
I didn't think of that. I guess it's a good point for me to pick up on that. I'm assuming yes. However, the thing is that it depends also on the program that I'm using. Right now I'm using YOLO 11X, which is like really the most accurate, and that does take some time. If I use YOLO S, which is the smaller version, then it gets faster. It does, but unfortunately it doesn't encapture the movement correctly. So it's also a bit of how accurate you want to have your results.
Mm-hmm.
Couldn't you like combine those 2 models, that you have like the lower frame rate in the slower model, so that the more accurate model does not work that long and the faster model works with the more data?
It is on my plan to do, but however I wanted at least the data set to really have the most accurate, because I wanted to have clear understanding if the program can detect each movement.
Yeah.
Especially when we have like this association, which are not always like, for example, if I go to voleo backwards, this is maybe can be a bit more visible, but here I am in front of the camera and I can do it. But if I am a bit on the side, I need to have 3 cameras, and the cameras really need to capture the leg. It takes a while. So for example, this is the real move that I will have on my own, and then we will wait a bit until this one, and still the leg will not go very fast because the program doesn't really, certain moves they are a bit more tricky to do, for example. So yeah, as you see, it takes a while, but as I said, at least for this part, I really wanted at least the data set to have a lot of high accuracy, and then when when users upload a video, I can have a smaller
Good, we have to move on, thank you. Let's move on, next.
Hello everyone, my name is Helmut, and today I want to talk about a problem which every C++ developer faces. So to help and address that issue, I worked on a solution So my project has a long title, LLM driven C++ developer tooling. So I can just tell you in short like what it is. So an LLM or a large language module is a kind of technology which is behind ChatGPT, Gemini, and Claude. So which is trained on a lot of data sets, which includes images, videos, text files, media files, and every kind of files. So to give you a better result. So when I say multi-dimensional, I just mean that the tool checks your code in many ways, like is it fast, is it safe, or what kind of performance it gives, in how many times it compiles as well. So I built a tool which lives in your IDE, for me which is VS Code. Okay. Okay, let's start with why this matters. C++ is everywhere. It runs on billions of devices, like your phone, your browsers, most of the cars, and even on the Mars rovers as well. It's very powerful, but that power has a cost. Like you manage your memory yourself. As soon as you expand the code, like the things get complex, and there's like so many complexities as well. So like you need to manage everything by yourself. So I wanted something different, one AI helper that checks your code after you have written it in multiple ways, in many ways at once, like without leaving the code editor. So yeah, so I was using this. Okay, this project has like two parts, one which lives inside the IDE, which works as an extension, and there's a backend as well, which works as a Flash backend. So I'm using Gemini 2.0 Flash for this one. Okay, I'm not the first one to point the AI to the code. So let me tell you where my work fits. So in the last few years, AI modules have gotten very good at understanding the code and debugging, and also making some test file as well. But all of these they have some limitation as well. Whenever your project expand to multiple files, so they don't know what they said previously, they lose the context. So that was the main gap which I can work on this area as well. So there's also some older approach as well, like static analysis, where tools study your code without running it. They're accurate, but they have a limitation. It's very difficult to set them up on your machine as well. So, you can see the table on your right. They're I compare my tool with the other tools, extensions, which lives inside the VS Code. So there's a limitation in every section. If you see in C++, some of the tools give you a good code quality, and then some of the tools use a LLM, and then if they live inside the IDE, they can make tests or they can support multi-files as well. So let's talk about the resource gap, which I found by looking into multiple tools out there. From that gap, I wrote three research questions. One, how can LLM be effectively integrated with traditional C++ tooling, like compiler execution, to provide advanced analysis? And the second question, to what extent an LLM-powered assistance improve developer productivity and code quality across the software development lifecycle? And what are the key challenges and limitations of LLM for C++ and generation? And how can they be mitigated? So this is my a project architecture overview of floor. So from the left side, if you see, there's a VS Code extension. So whenever in a VS Code extension, you click on the extension, and there are bunch of features. Whenever, for example, if you choose to explain the code, you use the code part. If you want to AI to explain it to you, so use the code part and click on the explain this code, and then it sends to the Flask backend, and then Flask backend communicates with the Gemini API. and then it gives you result in in JSON format, and then some of the time the output result is not good. So I have to clean that result and then parse this to the VS Code extension, so it shows you on the extension side, on the VS Code side. So this is the whole architecture flow, and this how it works. So to give you a better understanding what my tool does is, so I have divided the tool into 4 groups. So first, there are 15 analysis features which are currently working. First batch does is understanding the code, you can explain contextual QA chat as well, and logic simulation as well. There's AI transparency as well. And the next batch is run and verify, and third is improve code quality, and then review at a scale, if you want to do the analysis of the whole code base as well at the top. So the more I was interested in was in the run and verify, because there was test suite runner where it generates tests again the code. So yeah, that was my main focus area. But yeah, all of these other features works as well. So I performed around 150 test cases, different test cases, and the compilation score was around 98%. So, but around that compilation after success, only 95% of they were executing, these tests were executing, and there were so around 75% to 85% were which were compiling, and they were passing as well. And in 90% of the test cases, it was correctly extracting the symbols, and correctly, for example, if the user was using a contextual chat, for example, over here it mentioned contextual QA chat in the first batch. So if the user selects this function, how does it work? So it was extracting those things with the 90% accuracy. So it was extracting these features. So I did these below table explain into different functions. I used bubble sort as well, matrix and NQ and Fibonacci. So I compared their times as well, how much time they use, and the peak memory and CPU time as well, how much time they took as well. And then afterwards, I did a qualitative assessment as well with the different features. So I gave these features these are hand-based rating, so which I gave to these features. So natural language explanation got 4.5 out of 5, and you can see the rest as well. So they're somewhat near to 4 or 5. So at the end, I clearly addressed these 3 questions which I explained earlier, how my tool better fit for these questions in these areas. But there are some limitations as well. For example, if I have a very large code base, so yeah, as to the other AI models and these other tools, it also loses the context as well. So I was planning to use RAG implementation as well into this one, so it doesn't lose the context, and it also remembers everything which we have done previously. Yeah. Thank you so much.
Thank you. Are there any questions? If not, I think we have to move on. So we're lagging behind.
Hello, my name is Mohammad Hassan Malik, and my project is a safe, empowering and motivating cognitive support application. This is basically application for the people with the severe cognitive disabilities. And my main application, it's grounded on the self-determination theory. what basically the project is. It is basically a full stack app helping people with the severe cognitive disabilities, help them to manage daily tasks, communicate with each other, and also with their caregivers and with their loved ones. And also they can keep a personal journal of the activities that they did, and what, so that they can have like a memory lane when they see that. And basically it has two roles, caregiver and the patients. Basically both of them have their own separate dashboards, and the caregiver can manage the patients. They still have the autonomy, but to some extent the caregiver do manage the patients. The engagement layer must stay safe, helpful, and non-addictive, because if we see the gamification, if you want to create the motivation, you need the points and badges system to keep the people motivated and like so that they can use it again and again. But this thing creates dependency and anxiety. But for these people, we can't do the same thing, because these people are already vulnerable, so we can't make something that can anxious them more. So that's the main tension that we will break down in my project later. I read some research papers, and I did some literature, the Bachelor, like how the things are. So it gave me like three main important things, that gamification does help with the learning and with the cognitive behavior and increasing your life skills. But the most important thing is that the feedback matters. Like feedback, if you create a feedback, it can create it can be beneficial. And the second thing is the self-determination theory. It's like the motivation grows when there is competence and autonomy and relatedness in the application that you are building. And there is also a dark side of the gamification, like the streaks and the leaderboards and the badges. It creates anxiety, so we have to keep that thing in mind also. If you see the chart, 46.7% of all that the research in the gamification is related to learning skills, and 33.3% is the cognitive skills, and only 13.3% and 6.7% is personal behavioral or life skills respectively. So my main research in that area, where there is like very little research. So my main question is, the research question is, how can gamification enhance motivation and skill development while respecting the vulnerabilities of user with severe cognitive disabilities and avoiding addictive extrinsically driven design. So the socio-emotional skills, that matters a lot, and these people, they can't express their feelings and they can't build the relationship, because they are they face anxiety and other mental issues. So what my app does is it creates an environment where you can communicate with the caregiver. You can also do the practices. You can feel like you can be genuine in the app, and you can feel like you can be how you are. You don't have to pretend, or you don't feel like this. Little guidance exists on gamification that motivates without documented addictive risk. With the gamification, you have to keep in mind regarding the addiction. So we will keep that in mind while building the app. There are three pillars. The first is the feedback practice, second is the task management, and third one is the personal journaling. In the feedback practice, you can either upload your photo, you can either upload a video practicing. There are also some practicing sentences which you can practice, and if you want, you can send these practices to your caregivers, or you can also save them in your journal if you want to have a memory later when you want to see. And the second thing is task management. The caregiver can give you tasks, and they can also break the main task into subtasks. And when the task completes, either you get a reward of the caregiver by picture, like caregiver is giving you a thumbs up, or a video, like a motivational video, so you feel motivated that you have completed a task and you keep on. And the third thing is the personal journaling. You can create a journal of like what you did every day. Either you can include your practice into the journal, or you can just have like create like a log into your journal, or you can just say that how I was feeling today. If you want, you can share this journal with your caregiver, otherwise you don't have to share it. The app is basically built on the Angular as a front end and Hono Node.js backend with PostgreSQL and JWT authentication, and we are using the encryption because we are handling with the sensitive data, because that's of the patients. This is how the application, some screenshots. If you see the patient home, it's like a large icons and really simple interface, so that they can easily understand. They don't have to put strain on their mind in order to understand how the application works. So it's really simple. And we have also included the German extension. Either you can use English or German, so it comes with 2 languages. And if you see the feedback practice, like I told you before, it comes with predefined some feedback practices, sentences, and you can also upload a photo, and you can either record a video or a voice, like practicing yourself, or you can send it to your caregiver. If you in the caregiver dashboard, you can create a patient, you can like write details of the patient, and in that details, after you created the patient, you can assign tasks, you can also create subtasks. And one more thing, there are some tasks which are like really difficult. You can just not assign these tasks to them. First you have to create like a practice session for it. So you can also create a practice session, like there are some difficult tasks, you can create a practice session, and it will be like after you have practiced 3 times or 4 times or so on, after that you can do the main task. And it also gives you a qualitative trends. If you see it's written finish 1 task this week, it will just give you a qualitative task. It will come on the caregiver dashboard that this patient, he completed these many tasks this week, and he's like adding into the journals and doing entries and this and that, either he's quiet or not. If you go like in detail into the how things work in the application, basically it's Angular application with 2 roles, patient and caregiver. And if you see the JWT token, it goes to the backend, to the Node.js, and over there it verifies the JWT, and then it goes back and forth with the databases, with the media files, and all of the videos and photos are stored in the media files, but they are encrypted, so no one can view that. And also there is another thing, I included the Cloud API for the feedback reward. It will create like a cheer up message after you have completed the task, and I have put some like prompts into the code so that it gives like a good prompt, not something like which can make these people anxious or something like this. If we go into the reward system, as I told you before about the SDT, the self-determination theory, so these 3 things are very important: competence, autonomy, and relatedness. in the competence, like it gives you a calm AI message where I'm using the Claude. It also gives you a concrete photo symbol, like the photo of your loved one or caregiver. It does not give you any extract badge because it's like useless. And if we go into the autonomy, caregiver can also add some rewards. Like if you interact with the application, you can get these rewards. These rewards can be anything. Like it depends on the caregiver. They can either add like a sandwich or something like this. They have this option. They can do that. One more thing, relatedness. It can also when you complete the task, it will just pop up some cheer videos of your caregiver or loved one, so that you feel like more motivated and cheered up after you have completed your task. And it will also notify the caregiver that you have completed the task, or you have did something in your life, or you have added a journal or something if you wanted the caregiver to know. So like it will make them happy, that like how we use I was in the child, I used to tell my parents that I did this, I did that, and I used to make me happy that like I did that while telling my parents. So it's like this, that when they will tell their caregiver, so they will feel happy that we have achieved this and that. And the design iteration, I had something in my mind regarding the design, but after I did some research, I studied the research paper. So I changed the design a little regarding that count-based reward, which I removed, because the count-based reward is not good for these people. Instead, we are using the photos and the cheer up videos. And if we go, there is no scores and charts in the patient dashboard, because they can't really know what's happening by looking at the charts. So there are some qualitative trends in the caregiver dashboard and some maybe little bit charts, so that they know how well their patient is doing right now. And there is no streak system or like builds emotion which causes anxiety. As we know in Duolingo, it creates, you have to do the streaks, otherwise the bird dies, so it creates kind of anxiety. So whenever you feel like opening it or using it, you can just use it. And it gives you like autonomy. Whenever you feel like sharing the stuff with your caregiver, you can just share it, otherwise you don't have to. We have done 2 to 3 workshops with real patients in the hospital. I am working with a company in Dupendo Gambe, so they already have 1 or 2 application regarding these people. So in coming days, we are having another workshop where we will test this prototype, so that we can have what we can measure is like accessibility and ease of use for the patient. We can verify our STD theory, and we can see how motivated and engaged they are after using the app. And we can also talk with the caregiver, and we can see and we can ask them, is it really helping these patients or not? So the conclusion is like what we have I've done so far is I have the working prototype, and all of the prototype is based on the theory, self-determination theory, and basically we are targeting the socio-emotional expression of these people. And the next step is the evaluation, which the workshop that we will have in coming days, so that we can test our prototype and further we can launch it. Thank you.
Thank you. Any questions?
With which institution are you holding the user study, or how is it?
I don't know about the hospital, but my company, Independent Gambe, they arranged them. Yeah.
So it's you have also a partner company.
Yeah.
Okay.
Mm-hmm.
One second.
Flashlight.
I can
Yeah.
take it to it, sorry. I'm so sorry.
Hello everyone, my name is Kalian Danzer. My master thesis was about exploring WebGPU as a foundation for a game engine and teaching tool. And the scene you can see is the main demonstration scene that I used. And yeah, the motivation was that there are a lot of graphic APIs. They are all very powerful, but also all very complex. Didactics, for example, is kinda outdated. That's why Vulkan is coming up, and Metal on Mac, of course. But Vulkan has a lot of complexity and especially a lot of lines of code to achieve not that much, and thus is a steep entry for learners. And WebGPU promises essentially that you have still the explicit GPU control, but with way less overhead, and it's also cross-platform on each operating system, well, all of the common operating systems, and also works in the browser. Even when developed native, you can use mscripten to convert it to WebAssembly. Even though this is not fully functional yet, it works mostly. Yeah, but the main problem is, as WebGPU is still in development, there are very few completed engines, and there's almost none teaching material. There are like some engines using it, but the API is hidden, of course. There are some render tools, but there again the API is hidden. There are some open source ones, but not that many. And besides that, there are only experimental projects like the Learn WebGPU, which was very helpful during development, and some sponsored demonstrations to show the performance gain over like WebGL. Yeah, and that also is like the related work, other engines, web graphics, some teaching graphics, and yeah, especially like those common tutorials where you learn like how to create rendering. So the research gap is essentially that we only have WebGPU demonstrations and some isolated tutorials, a few experimental renderings, but what's missing is a modular engine where you really have it designed for education. Like most of you probably know the Vienna Vulkan engine, and for WebGPU something like that is not existing yet. So there were 3 research questions, especially like what is the current state even currently, as it's still in development, and thus if a full functional game engine can be built on top of WebGPU, and most importantly if it's less complex and engine with the focus of education can be built on it, which also were 3 hypotheses derived from. If WebGPU needs less complexity than Vulkan, complexity was in that case the lines of code. Yeah, then if the tutorial yields self-assessed learning gains, and if the learners perceive the material as useful. So the Vienna WebGPU engine works on all systems. It has a layered architecture with different namespaces, and have the handle system, so you don't work with raw pointers. It uses a scene graph as most render engines. It's node based, somewhat related, like it's in Godot engine. Not exactly the same system, but I guess it's the nearest one. and it uses shader reflection. The teaching, or like where the tutorials came from, and were built on used manual reflection. So you like described via code what the shader already wrote, but like way less code than you would need if you really described everything yourself. So the engine already does the heavy lifting. The current version, which I further developed, but the tutorials were not built on, already does it even better, that it actually tries to get the data from the shader file, which is the VGSL language, which is WebGPU specific. There are not that many tools to translate to like other common shader languages, but there are some still work in progress, as WebGPU is still not finished. And yeah, you can see the scene before and post-processing, which is the fourth tutorial. And yeah, it's multi-pulse rendering, and there were some challenges, as there were not that many WebGPU examples, so I had to translate a lot of stuff from OpenGL. And also that there are like different conventions, as OpenGL uses -1 to 1 as depth, and WebGPU uses 0 to 1, and also the coordinate system is flipped. And yeah, some backend validations during the testing, as some of the evaluation was done on Mac, and yeah, the metal is more strict on the bind group ordering. So when developing on Windows, I did not notice that yet and had to fix it. And yeah, essentially the evaluation was done via a mini course of 4 tutorials. The shadow mapping one was kind of left out for time, because the evaluation was tried to be done in under an hour, or around about an hour. And with the tutorial 1, 2, and 4, most of it was covered already, and they tended to actually needed more than 1 hour, like more than 1.5. So yeah, the third one, after the first test, where the first subject already needed more time, I did not create the third one, but it would be something for the future. And you can see the second tutorial here, like the guided approach, worked example approach. It's like you could copy paste the code on each step and just do it, but it's encouraged to like read all the explanations in the tutorials, and it will actually tell you what you're doing. And it's a common approach in rendering, like Unity does something similar in their tutorials. You see the images and can look if you're doing it right. And for the evaluation, it was more or less 2 parts. One was the ecosystem assessment, as there was a lot of changes during my development, as it's still in development, of course. So first, when I created it, it was also with the web focus, which did not work after some updates anymore, so I paused it and focused on the native development. Nowadays, there's a more stable than the default emscription. It's the Google Dawn emscription one. But yeah, I did not manage to work with it yet, because it's a lot of different build tools, and they're not for all platforms. But yeah, the assessment was how it changed, and the lines of code. And as you can see, Vulkan has more than twice the lines of code, way more API calls, and way more functions. At least the cyclomatic complexity is the same. But if you are first coming into rendering and trying to learn something, and just to render a simple triangle, you have to write 700 lines of code and understand them. It's not very helpful. And for the user study, it was 2 parts. It was first assessed like how everybody felt about their knowledge on a 4-point Likert scale, grouped into those sections, as you can see there. And then again after it, and overall there was good improvement. And then also what they reflected on themselves, so what they thought about the tutorials and how it improved their
learnings, and if they would recommend it or if they did not help them. And yeah, there were 15 participants actually, and overall they agree that the tutorials helped them, and also their subjective learning gain. Important, it's only a subjective learning gain, so there was no like test or something. Was also quite good and also relevant as the p-value shows, and even the Vulkan p-value shows. Thus the hypotheses were all supported. And yeah, for the future work, especially the web deployment would be interesting, and broaden the cross-platform, especially as I moved to SDL3 recently. So I would need to validate if that works on Linux and macOS still. Expand the tutorials, like covering more, especially after I now changed some of the code, and doing a larger study beyond just the self-reported gains. As yeah, it's nice to have, but having actual tests would be quite useful, of course, as well. And yeah, here are the most important links of the repository, the main source, and the rendered scene. Yeah, if you have any questions, you can ask them now, and I would have a demonstration as well.
Thank you. So set up the demonstration, I would say. Are there any questions regarding this engine?
So we can see the performance here, for example. On the big screen, of course, it's less, and also in the notebook than at home. And there's not that much performance increasement done yet, besides clustering the lights. So if you see it correct, yeah, I created a light flock. So even like thousands of lights can be enabled with still somewhat good performance. The clustering is a bit buggy still, because I just recently developed that and moved from the forward rendering to like the cluster deferred rendering. As with forward rendering, you will not achieve more than like 5 lights on somewhat performant. And if you actually want to render that many lights, you need to change it. So I did that, and a lot of debug values, so you can really inspect it and look into the different passes, reorder them, disable them, and also like different scenes. That's like the first demo scene actually, and you can configure different lighting in this UI and look into that values, or like enable and disable the skybox in the background, and yeah, just in general look how this everything connects. You don't see it now, but there's also a lot of output logs, by default only the debug output logs, but in the background there's even more which is traced, so if you really want to inspect it and go into it, yeah, you have the possibility, and even see what needs how much performance. So even the main demo scene was very focused on people to try it out, see what they can change, what happens. Yes.
I would have a question. So what exactly was it that you built? Did you build the engine by scratch?
Yes.
And the target was for it to be a learning engine?
Yes.
Okay.
So it's I can show you, it's a lot of files by now. It's even more, so that's not like all of the files, which is also why there is a lot of documentation files which really try to narrow it down on what to do, which is also the reason why there is like the tutorials explicitly. I can show it to you here, really telling you where to change what and trying to explain why some things are located at some locations. Also trying to make you understand the concepts of those, especially for the post-processing, why is it located there, or like for the structs, why have they to be built like they are built, with types and such. So it's obviously a difficult topic, and it's not something for beginners probably, but as the tutorials have shown, even beginners, so some of the participants had no prior knowledge about rendering, and even those could actually gain some value out of it. And it tries to encourage you to explore the engine, which is of course big and has a lot of content, but that's also the reason why I chose to have that many files, is that you can actually focus on each thing separately, because for me personally, working in a big file with like 3,000 lines of code, I don't understand anything anymore at some point, because it's just too much information at once. And here it's like the include files and the headers and the CPP files also separated. In the headers there's all the documentation and why it's done what way and stuff like that. And then in this CPP files it's actually just the code on what's done, with some inline comments explaining why stuff is done like that.
So it's a WebGPU engine built for users to learn how WebGPU works.
Yeah.
Okay.
And also how rendering works in general.
Oh, rendering, okay, based on WebGPU principles.
Exactly.
Okay. Cool. Thanks.
Thank you. Yeah, let's move on. We have still 2 presentations. Almost there.
Perfect. Well, my name is Ruslan Shakir, and here's my practical course 2 progress report. I've been working on implementing the ray tracing renderer for Vienna Vulkan engine. So the previous state, I'll be quick about Vulkan engine on rasterization renderers. The forward, we basically turn the ball we usually work when taking courses from gaming track, and the deferred one may be incomplete. I couldn't really make it work, but it was always ray tracing the engine planned. So what I did first, I tried to port our RRT engine to somehow fit it into the Vulkan engine architecture, but maybe some of you took the real-time tracing course and you've seen the RRT engine. It has, at least pretty much on its own, has a very different dancing pipeline. It has different ray tracing pipeline. It, as far as I understand, it uses compute shaders instead of ray tracing pipeline. It basically just doesn't use the canonical Vulkan approach for ray tracing. So the second attempt, I tried it from scratch based on the Vulkan NVIDIA's Vulkan ray tracing tutorials. Wrote a new render for Vulkan engine which fits pretty well architecturally into the current version of Vulkan engine, with shaders written in Slang, unlike RT. And the pipeline is very high level, looks pretty much like that. We first query ray tracing extensions and capabilities, because we need hardware accelerated ray tracing. We build acceleration structures. It's done carried out by Vulkan implementation, although telling Vulkan to do that maybe requires more code than writing it by hand sometimes. It feels like that. Okay, then we build shaders to the pipeline. With shader binding tables, we also bind the resources, textures, material information, lights information, then dispatch, update all the bound resources, and then again repeat. This is still FIFO complete. There's some stuff to do. Implement path tracing because currently it's a weighted ray tracing implementation. There's still some performance optimization. For example, update acceleration structures is just possible instead of rebuilding them every frame. And still there are some minor bugs that still could be fixed. And further work that could be done based on this ray tracing renderer, like could be implemented advanced techniques like temporal anti-aliasing, restore, upscaling, then ported onto ongoing build of Vulkan engine version 3, and maybe also adapted for a real-time ray tracing course, so the students will have unified experience across all the gaming track courses and also have hands-on experience with the more canonical pipeline of interacting with Vulkan ray tracing. So there are not so much left to tell. Let me just show you the quick demo. I built a pretty basic demo. Here is the test VVE target with modified. I removed the grass texture, and here we can see it's the old forward renderer. I added like 10 lights that are like circling and moving in a circle, and they are colored pretty much like a rainbow. If you fly a bit further, you can more or less see it. And yeah, this is pretty much the familiar look. So far there are no shadows, but it works, and it's pretty stable. It shows pretty good results. But now we can try it with ray tracing. Now we can see there already appears the shadows, so that's, you can see how the lights are moving. Just for the demonstration purposes, I gave the spheres the reflection, so you can see, and the recursion is not very deep, so we can see some artifacts, but it works pretty well. The small assets are also rendered pretty fine, and yeah, and the performance actually is even a little bit better than forward render, because forward render chokes a little bit on too many lights, and so far that's what I can show you.
Good, very good.
Any questions?
If there are no questions, then we will move on to the final presentation.
So hello everyone, my name is Vulkan. So today I'm gonna present my project, Lock-Free data structure in modern game engines. So to understand why this matters, we have to look at the golden rule of the real-time rendering, the 16.6 milliseconds frame budget to run game at 60 frames per second. The CPU has exactly 16.6 milliseconds to calculate physics, AI, and game logic before handling it off the GPU. So today I'm gonna talk about how traditional software architecture fails to meet that deadline, and how Lock-Free programming provides a solution. So single core CPU speeds fluctuated for a decade ago to get more performance. Modern game engines like Unreal and Unity moved to highly parallel job systems where thousands of microtasks are distributed across 8, 16, 32 worker threads. So the problem is how those threads communicate. Traditionally, we use a standard STD mutex to protect our shared data, but if an AI thread works the queue, the physics threads gets put to sleep by the operating system. So waking it back takes thousands of CPU cycles and massive waste of time. Alternatively, we can use spin locks where the thread just loops in place, but this burns CPU cycles, generates immense heat and scales poorly. The foundational related work to solve this problem is the Michael Scott Lock-Free queue introduced in 1996, which proved we could build a first-in, first-out queue using atomic hardware instruction instead of locks. So, however, applying standard academic lock-free structure directly into game engines reveals a massive gap. Most standard lock-free queues rely on dynamic memory allocation, calling new or delete when a job is added or removed. In a game engine, dynamic heap allocation in the middle of the whole gameplay loop is disastrous. It destroys CPU cache, coherence, and causes unpredictable stalls. So my core research question: can we build lock-free queue, deliver deterministic sub-milliseconds job scheduling under heavy multi-core contention, beating mutex-based alternatives? So my solution is lock-free task queue, driven entirely by CPU level hardware instructions, specifically compare and swap. Instead of locking the queue, so only one thread can use it, multiple workers simultaneously attempt to update the queues, head or tail pointers. The compare and swap instruction acts as hardware level check. It says only update this pointer if no other thread has changed since I last looked at it. If another thread beat them to it, the CS fails and the thread instantly loops to try again. That thread never goes to sleep. There is no context switching, and mathematically guarantee that at least one thread is always making progress. So my implementation, so far I implemented core structure build like baseline Microsoft lock-free queue. I built it from scratch in C++. I also made atomic operations down. Also compare exchange with CAC loop and safety mechanisms and also testing environments are done. And for the further, I'm going to implement in queue the queue pass. Like how it's going to be. First, like the one worker thread will be the header pointer, and one worker thread will take the tail pointer, and when they need to take job, the header thread will take one-off job from the job queue, and when the new job is added, the tail pointer will check if the for example the last job has been added or check it if it has been notified since they added the job. So let's go to the next one. So overcoming the memory trap. While getting CES loop working was a milestone, it immediately highlighted the hardest part of the lock-free programming, memory management. When using standard time allocation, you inevitably hit the ABA problem. This happens a thread reads a pointer, gets paused, and another thread deletes and reallocate the exact same memory address. The first thread wakes up, sees the same address, executes the CAS operation, and corrupts the entire queue. To make this truly engine ready, my strategy eliminates new and delete entirely. Instead, I'm reallocating a massive dense array of job nodes at startup by using static array indices instead of raw memory pointers. So it naturally mitigates the ABA problem and maximizing CPU cache hits. Initial results to evaluate if this architecture actually solves our 16.6 milliseconds problem. I'm testing it against standard ST mutex, Q, and atomic spin lock. So the test simulates one producer thread and 8 worker threads processing more than 100,000 engine jobs. So till latency, the maximum time and single thread was dealt. Our expected results show that under low condition, lock and lock-free perform about the same, but as we scale up to 8 thread, the mutex queue experiences massive latency spikes as the operating system struggles to wake the sleeping threads. So the lock-free CAS queue, comparing SWAP queue, combined with the pre-allocated memory, maintains a completely flat, predictable execution time, proving it's necessary under high load. And in conclusion, relying on the traditional synchronization is no longer viable for modern real-time rendering. Lock-text data structure utilizing CAS atomics and strict pre-allocated memory. So the trade of the discourse I'm trying to implement the C++ 26 concepts like segmented vectors to allow the queue to safely grow without reallocation penalties and potentially implement work stealing so idle threads can lock-free take jobs from overwhelmed thread. That's all.
Okay. So how do you tackle the ABA problem?
Actually, I would also like to make it with the microscope algorithm. The ABA problem is, for example, if the thread A reads from the data, and at that time thread B changed that data while the thread A was making it. For now, I just make it done by synchronize the system, like the operation. But for the future, I'm gonna think about some other things because it will really, it's not like time efficient for now because while one thread reads one operation, the other thread should wait since the other thread should be done. But yeah, for now I'm gonna think about it. But I'm also thinking about adding the whole jobs to the job queue. That, for example, how I said, the tail head pointer reads from the job queue and check if it's if the thread hasn't done their job, it will still the other thread will go to loop and will do another jobs, and then when the thread A is done, it will come and take that value to process that value.
Well, one easy way to tackle the ABA problem is to use generation counters inside your handle, because then every handle is different, even if it points to the same item. Okay, you're not using pointers, but you're using a handle, and part of the handle is an index, and the rest is a generation counter.
So like how it's gonna work internally, it should like
Because you run into ABA if you reuse the same pointer.
Yes, exactly.
Exactly. But if you use a generation counter, there's no, the handle
okay.
will never be the same.
Okay, got it.
Okay, when you use, when you try to reuse something, or when you try to dequeue something, you simply increase the generation counter.
Okay, so basically they will have ID.
It's an ID,
okay,
exactly. Right.
Got it.
But part of it is an index. So the index tells you where it is in the array, and the generation counter tells you, is it the same item we're talking
okay.
about? So if you read the current handle of the next thing, and then the thread goes to sleep, which is the big problem,
Yes.
then somebody else grabs the handle, but by grabbing it, it will change the generation part. When the initial thread comes back and it tries to cast, the handles are different. Okay, so that's the idea.
Okay. Yeah, I will implement it.
Think about it. So,
Okay. But still, like the ABA problems.
yes,
it's not
very,
like
very
fully
tricky one.
implemented yet, yeah.
Very tricky one. Okay, good. Okay, thank you.